All right, well, welcome back to today's lesson on integrals part two. So in the previous lesson, we had a look at the area under a curve. So we basically had a look at how do we actually define the definite integral. So we first had a look at how to, what happens when we break up um, the area or under the graph into rectangles, in which we concluded that, well, when we have more rectangles involved, we would actually get a better approximation. And whenever we have a infinite number of rectangles, this would actually give us um, a very precise area, which is going to be the exact number that we're actually looking for. So we had a look at the integral here. Um, We also had a look at the basic properties of the integrals here. We had a look at the two theorems called the extreme value theorem and the squeeze theorem. We also had a look at the fundamental theorem of calculus, part one and part two as well. So those will actually come into play whenever we have a look at integrals later on, uh, sometime in the future. So that's the fundamental theorem of calculus, part one. And we had a look at some examples as well involving this. And this is the fundamental theorem of calculus part two, where we just have a look at the f is the antiderivative, then we could find the difference between the twos to obtain such a number. And that was all from last lesson. So this lesson will continue on with the integral section. Okay, so this section will be having a look at the indefinite integrals. So we know that the relationship between the definite integral and antiderivatives. So they have some common similarities with each other. So to make things simpler, we say that the integral of a function is the general antiderivative. So that means whenever we have an integral of f of x dx, this is going to be the general antiderivative. So what does that mean? Well, the general antiderivative, if you remember from lesson one, we actually had a look at that. So this was the general antiderivative. So the general antiderivative is going to be this f of x plus c. So that's what we actually want to put down here in this section here. So we have that, well, f of x here plus c is the general antiderivative, or we say that it's actually the indefinite integral. So whereas this c, again, remember, is a constant. So where c is a constant. All right. Well, this symbol over here, if we don't have the bounds on the lower bound and the upper bound, we say that this is actually an indefinite integral. And we know that it has no lower or upper bounds. And also, remembering that, well, f prime of x then, if we take the derivative, this is also the same as the derivative of f of x. All right, so let's have a look at an example of an indefinite integral. Well, so we have the integral of x cubed plus 4x. So what we could do is use the summation property for integrals. Well, we could actually just break this up. So that this becomes x cubed dx plus the integral of 4x dx. Well, we could also bring out the constant here for the second integral. And then we could evaluate this right away. So for the first one, we would just have a quarter x to the power 4. And then for the second one, we would have 4 by x squared, or 1/2, times x squared. Or once we simplify things a little, we would just get 4 a quarter x to the fourth plus 2x squared. And then this is going to be plus c. All right, so that's not really that bad. So it's always important to remember that we always add this plus c at the end. It's very important that we do not forget about it. So the general result of an indefinite integral is another function. So we assume that the result is going to be valid for a certain interval. For example, if we take the integral of 1 over x squared dx, which is also the same as saying, well, this is going to be the integral of x to the power negative 2 dx. But that's also the same as saying, well, negative 1, x negative 1 plus c, or negative 1 over x plus c, right? But so visually, this is what the graph would look like. So say that we have this graph here, which is the 1 divided by x squared. But we also note that, well, if we assume that the result is valid for this region here, but noting that as well, we have a vertical asymptote at x equals to 0. So there's a vertical asymptote at x equals to 0. So that's what we could assume here. But let's see what happens when we evaluate 1 over x on between negative 1 and 1. So visually, so if you want to visualize this, so we have one function or one direction going this way, the other going this way down here, right? So if we want to find the area, we want to find between 1 and negative 1. So we calculate this area, and we also calculate this area over here. Well, here's the thing. If we compute, well, I'm going to break up the interval so that we can actually evaluate from negative 1 to 0, and then from 0 to 1. So that was one of the properties that we had a look at. So between negative 1 and 0 of 1 divided by x of d of x plus the integral from 0 to 1 of 1 over x dx. But once we evaluate this, well, this is actually just going to be the natural log of x evaluated from negative 1 to 0 plus the natural logarithm of absolute value of x evaluated from 0 to 1. However, there's a problem here. We cannot evaluate this integral or this value at 0 because remember, ln of x only exists whenever it's greater than 0. But let's see what happens when we actually let a value approach 0. So let's say we let t. So suppose we let t approach 0. So what that means is if we have the limit here as t approaches 0, for the first one, so we have ln of x, absolute value of x, evaluated from negative 1 to t, plus the integral or the natural logarithm of x, evaluated from t to 1. Okay, so let's put all of this in. So keeping the limit as t approaches 0. So that means we would just have ln of t plus minus the limit as t approaches 0 of ln of absolute value of negative 1. So that's important. We need this absolute value of negative 1 here, plus the limit as t approaches 0 of the natural logarithm of 1, plus or minus the limit as t approaches 0 of ln of t. Well, two things here. We see that, well, this value is going to go to 0. This is value going to go to 0 because ln of 1 is 0. Well, as ln t is approaching 0, we would get positive infinity. So that means if it's going to go to 0, it's going to be going to negative infinity. Yeah. And if we put in from the negative side, it's going to go to positive infinity. So that means the result here, so we just have the limit as t approaches 0 of ln of t minus the limit as t approaches 0 of ln of t. Well, that's just going to equal to 0. Or another thing that we could see is that these end up canceling out with each other. So that means the area under this curve is actually just going to be 0. All right, so let's have a look at some more examples of integrals here. Okay, so let's say we want to compute the following integrals. So for the first one, we have the integral of sine x minus cos of x. We could break this up into two separate integrals. So for the first integral, we would have sine of x dx minus the integral of cos of x dx. Well, if we put this in or evaluate each of them, so for the first one, we would just get cos of x plus sine of, or the second one, we get minus sine of x, and then plus c. And that's all we would have to do for this one. Not too bad. All right. As for the second one, though, it's also important to realize that, well, sometimes it's actually easier to break up the integral into its individual fractions. So see in the denominator, I could actually break this up into this fraction. And then for the second fraction, I have this fraction here. So that means I could actually rewrite this as 2x cubed divided by x squared dx minus, yep, the integral of 3x divided by x squared dx, which then leaves us with the integral of 2x dx minus the integral of 3 over x dx. So evaluating each of these integrals, we would just get x squared for the first integral. And as for the second one, we would just have 3 ln of x plus c. Okay. As for the third one, well, we have a definite integral this time. So this one will need us to use fundamental theorem of calculus part 2 to actually evaluate this. So first of all, separating the function into two separate functions. And so we could also subtract this 0 to 1 of 1 divided by 1 minus x squared dx. So the integral for the first one is just going to be 1/3 times x cubed. So that one, we would just have 1/3 x cubed. And as for the second one, well, we would just have, so this is evaluating from 0 to 1. For the second one, we would just have sine inverse of x from 0 to 1. So for the first one, well, that one is just going to be 1/3, because if we evaluate the one at 0, it's going to end up being 0. As for the second integral, well, let's have a look at sine inverse first. So we would have sine inverse at 1 minus sine inverse at 0. Well, the first value, if you put this into your calculator, you would see that this value is actually pi over 2. But as for the second one, this would be just 0. So that means this integral would just be 1/3 minus pi over 2. And that's all. And as for the last one, So part D, we could do the same thing what we did in part B as well, where we just separated the fractions. So for this one, we could write this as the integral from 1 to 3, x4 over x dx, minus the integral from 1 to 3 of x root x divided by x dx, minus the integral from 1 to 3 of 1 over x dx. And so from here, we could just simplify things a little. So we have integral from 1 to 3 x cubed dx minus the integral from 1 to 3 of root of x dx, and minus the integral from 1 to 3 of 1 over x dx. And so evaluating each of these integrals, we would just have a quarter x to the fourth from 1 to 3. The second one, we would have to be a little bit careful. So since this represents x to the half dx, so that means we would just have 1 half plus 1, x a half plus 1, which simplifies out to be 2/3 x 3 over 2 between 1 and 3. And then we have, for the third one, we have ln of x evaluated from 1 to 3. And so plugging in the values, so for the first integral, we would just have 81 divided by 4 minus a quarter. For the second one, we would get, well, 2 over 3. We get 3 root 3 for the value, minus 2/3 here. And then minus ln of 3. So ln of 3 minus ln of 1. So this value, we see we could cancel some numbers here. So these 3 cancels. This is going to go to 0. And so that means our final answer will just end up being, well, 20 minus 2 root 3 minus 2/3 minus ln of 3, or that can turn out to be 62 over 3, 2 root 3 minus ln of 3. So that's the answer for part D. So let's move on to the next question, or the next part. So now let's say you have the rate of change of a quantity. For example, velocity is the rate of change of the position over the time. Then the integral of the rate of change of velocity would pretty much just be the net change of the quantity, which is the position. So, for example, let's say that the velocity of an object is given by vt is t cubed minus 4t. So what is the total displacement of the objects from 3 seconds to 10 seconds? Well, one thing that we could find out is that, well, delta S here, which is going to be the total displacement, can be written as the integral from 3 to 10, so from 3 to 10 seconds, of the function v of t. So that's going to be vt dt. So that's going to be 310 of t cubed minus 4t dt. And so that is equal to, so if we could evaluate this right away, that's good. So that's, first one's going to be a quarter t to the fourth. The second one is going to be 2t squared. And we're evaluating from 3 to 10. And so here, we would just be a quarter 10 to the power 4 minus 2 times 10 squared minus 3 over 4 all this squared, or 3 to the power 4, and minus 2 times 3 squared. And so if you calculate all that, you would get about 2,297.75 units. So that is the total displacement. So let's consider the next example. So air is being blown into an air balloon at a given rate given by Vt, or V prime T, which is 3t centimeter cubed per second. So if the balloon is initially empty, what is the volume of the balloon after 5 seconds? Well, one thing we know is that the initial balloon initially is going to be empty. So that means V at 0 is going to be 0. We also know that dV divided by dt is given by 3t. So that means for the total volume after 5 seconds, it's going to be delta V given from 0 to 5, 3t dt. So that means we calculate 3t squared over 2 from 0 to 5. So that means 3 times 5 squared over 2 minus 0 would just be 75 over 2 centimeters cubed. So that's the volume. All right, so let's have a look at some more definite integral or indefinite integrals here. So for the first one, we could just use the sum property, expand to each of these integrals. So once again, this could just be integral of x cubed dx plus the integral of 6x dx plus the integral of dx here. So that means we would just get a quarter x to the fourth plus 3x squared plus x and then plus c at the end. And as for the second one, well, notice that in the denominator here, we actually know this identity here. So this one is also the same as saying cos squared of x. So we could actually evaluate this. So if we rewrite it as sine x divided by cos squared of x dx, well, that's also the same as saying sine x, or no. So we have secant of x, and we also have a tan of x here. But that is indeed the integral for secant, or this is the derivative of secant of x here. So that means the antiderivative is just going to be secant of x plus c. And that's all for this part. All right. So now we want to apply the knowledge that we know about integrals now with some techniques of integration. So let's have a look at this section. So sometimes it is difficult to determine antiderivatives with a lot of functions using the knowledge of differentiation rules. So this section will focus on the tools that we need to evaluate integrals. So let's start up with somewhat a simple derivative of a function y is equal to 1 plus x squared, all of that to the power of 3. So if we want to rewrite this, so let's say we let we're going to let the inner part be the function u. So this is the one that we're going to be doing a substitution with. So let's say let u be 1 plus x squared. But the next step here is that we actually have to differentiate both sides. So that means, well, d over dx is also the same as saying 2x. So that means, well, once we make the substitution for u now, so that means y is equal to u cubed. But let's have a look at this using the chain. Well, dy over dx is also the same as, well, df of u of du multiplied by du over dx. Or instead of df of u, this could be dy as well. Well, since df or dy over du here is just going to be 3u squared, so because if we take the derivative on both sides, that's going to be 3u squared. But so that means we would just have, so dy over dx is just going to be 3u squared multiplied by du over dx. So that means if we substitute it back into the original function, or actually we also know what du over dx is, which is just going to be, so 3u squared multiply 2 by x. But we also know that u is going to be 1 plus u squared, 1 plus x squared. So we could put that back in. So we have 1 plus x squared minus 2 of x. So we could apply this idea to compute some integrals. So I made some small mistake here. There should be 2 times x here. So that means we should have 6x here, not subtract. Yeah, so that's what the integral should be. Or the fy prime should be. Okay, so let's start with by finding the integral of this function now. So for this part here, note that, we often substitute for what is under the square root. So that's one thing that we could also make a note of. So we could make the substitution. So we're going to say, let u be 1 plus x squared. And then, so by differentiating both sides, we would have du dx, which is 2 of x. Or we could also rewrite this as du, which is 2x dx. But guess what? We also have a 2x dx on our integral. So we have the 2x and dx. So that entire thing would just become the du. So all that would just become this. So let's go ahead and put this all together. So 1 plus x squared is here. And then we have the 2x dx. So this entire thing inside the square root is going to be u, and everything here is going to be du. So what we see is that we have a root u du. And so now we're integrating with respect to u now. So this one here, integrating with respect to u. Respect to u. Okay, so once we integrate with respect to u now, so that means, well, we could use our standard methods of integration that we are familiar with now. We should get this as a result, and then plus c. However, we're not quite done yet. Well, we're almost finished. We're just missing one step here. The only step that we're missing is that we actually have to substitute back the 1 plus x squared into the formula. So that means we put back the 1 plus x squared in place of the u. So we have 2 over 3 times 1 plus x squared to the power 3 over 2, and then plus c. So that is the answer. So we do a substitution to make our integration easier, and then once we're done computing the integral, we put back the function that we substituted with. Okay, so this method of substitution works when we have an integral of the form. So if we have a function that is a function of u multiplied du over dx multiplied by dx. So it only works when we have some sort of form that looks like this. So this is the one that we're most likely going to be substituting or getting from. And this part is the function that we would get after changing some stuff around. All right. So let's have a look at some examples. So let's say we want to evaluate tan of x for the first one. Well, note that tan of x here, we could actually write this as the integral of sine x divided by cos x, all this by dx. So what's the substitution that we're actually going to be making here? Well, we're actually going to be substituting for the denominator here and this dx. Here's why. So let's say we let u be cos of x. Differentiating both sides, we get du over dx, which is negative sine x dx. Well, guess what? Well, let me rewrite this a little bit more so that we have negative du. Oh, there shouldn't be a sine x here because I already brought the dx on the other side, so that's what it's going to be. So we have negative du of sine x dx. But guess what? We already have the sine x dx. So this is the sine x, this is the dx here. So that's the one that we want to substitute with. So we replace the sine x dx by negative du, and the cos x, we replace it by u. So this u would become this over here. So putting everything together, we would just get the integral of negative du divided by u. Or if you want to write this a bit easier, 1 divided by u du, which looks like an integral that we could easily integrate. So that would just be equal to negative ln of u. So, and then plus c. So the last step here would just be to put back the u. So we would have negative ln u, which is cos of x. So absolute value of cos of x plus c. And that's all what we would actually have to do here. Or if you want to go ahead and simplify a bit further, so this one, we could also write this as secant of x plus c. Right? All right, so let's have a look at the next one. So for this one, we have x times 4 plus x squared, all that to the power of 3. So it should look obvious that what we actually want to substitute is this 4 plus x squared here. The one that looks a bit more complicated to work with is the one that we would substitute it, most likely. So let's go ahead and see. So if we're gonna let u be 4 plus x squared, then that means du is equal to 2x dx. Well, since if we see here, we only have an x multiplied by dx here, but we have a 2 that is in front. Well, the thing here now is that whenever we have something like this, we just want the function multiplied by this d of x here. So whenever we have some constant that is most likely unnecessary, we would just have to bring it to the other side. So we're going to divide both sides by 2 so that we get half of du, which is x times dx. So now we would just have this x dx, which we would just replace it by half of du. It would just go here. the u would just be going under the 4 plus x squared. So what this integral actually becomes, so one thing actually before we move on, we also have to change the bounds here because right now the bounds are with respect to x. So we actually have to change it so that we're making it with respect to u. So let's say when we we say that when x is equal to 1, so that means what will u become then? So that means u, so if we put 1 here, so that's 4 plus 1 squared, which is going to be 5, right? And similarly, when x is equal to 3, so that's going to be 3 squared, so that's going to be u plus 4 plus 9, so that's 13. So that's one other thing that we would also have to keep in mind. So this is also important. So if we put everything together, so we're going to change the bounds on the 1 and 3. So this is also going to be changing. So we have 5 and 13. The x dx becomes half of du. So I'm going to put a half on the outside. And then the u will be the 4 plus x squared. So that's going to be u to the power 3 du. So that means, well, half then of a quarter u to the power 4 of 5 to 13. Now, it's not really necessary to substitute back in the function when at this point you could just put it all in so that you wouldn't have to do, because really at the end of the day, we just want a finite number because it's a definite integral. So it would be a bit of extra steps if you put it back into, if you substitute the original function back into the integral. So all that means is we could just put, well, 13 to the power 4 divided by 4 minus, well, 5 to the power 4 divided by 4. And that would be some value that we don't really have to bother calculating as long as we get some value out of it. All right, so let's have a look at the last two examples here. So these ones would be pretty interesting to find. So let's have a look at what we're going to substitute for part C. So as we said earlier, we usually want to substitute anything that is under the square root. So that means we're going to substitute here this x, 2x minus 1 here. So I'm going to say, let u be 2x minus 1. Then that means du is 2 times d of x. But one thing that we're also missing here is that, well, here we don't actually have something with respect to x now. So that means, well, if we solve for x in this equation, so note here, sometimes we would have to find something with respect to x as well, or in terms of u. So that means here, if we solve for x here, we're going to get u plus 1 divided by 2. So this is the x. So this x that is over here, that is what we're going to substitute here. And so now we're ready to move on. Or actually, one more step. For the du here, we're actually going to write this as half of du. That is also the same as equal to d of x. And now we're ready to substitute everything. So the 2x minus 1 is going to get replaced by this u. The dx, this dx over here, is going to get replaced by half of du. So putting everything together, we would just get the integral of u plus 1 divided by 2, multiply that by root u of d of u. Okay, so now we could just find this. So that would just be u root u plus divided by 2 du plus root u over u 2 du. So this u root u is also the same as u to the power 3 over 2. So if we take the integral of this du, this is going to be, 1 divided by 3 over 2 plus 1, u to the power 3 over 2 plus 1, which ends up being then, so that's going to be 2 over 5, u to the power 5 over 2, right? And as for the second one, I'm also forgetting to divide it by 2 as well. So take this multiplied by a half. And we add by a half multiplied by 2/3 u times 3 over 2. So as a result, this would just be 1/5 u 5 over 2 plus 1 over 3 u 3 over 2 plus c, where c is the constant. Okay. So as for the last one, let's have a look at this one. So part D, we have the integral of x divided by x squared minus 1 multiplied by d of x, dx here. So once again, we also do the substitution under the square root. So let's see. So we're going to take this and substitute it. So we're going to say, let me use a different pen. So let u be this x squared minus 1. So that means du is 2x dx. And so we're going to bring the 2 to the other side since we only just want a x by dx here. So that means half of du is equal to x times dx. So putting everything together, we would just have the integral. So x dx becomes half du. I'm going to bring the constant half to the outsides. And then so we have 1 then divided by root u du. Okay, so that means now I have a half. This is also the same as the integral of negative 1/2 du. So that means we have the 1/2 multiplied by 1 divided by negative 1/2 plus 1 of u to the power negative 1/2 plus 1. So that now is also the same as the integral, or 1/2 multiplied by, so that's going to be 1/2, so that's going to be 2 x to the power 1/2. And so, or sorry, this should be u. And that would just be, so the 2's cancel out, we would just get u to the power 1/2. Or putting back the u with the x squared minus 1, we would just have x squared minus 1 to the power 1/2 plus c. And that would be this integral over here. Okay, so now let's move on to the next part. So many functions are symmetric about an axis or about a line. In such cases, we use the knowledge, of symmetrical functions to simplify definite integrals over certain intervals. So for example, let's say we want to evaluate the integral from negative pi to pi of sine x dx. Well, visually, I could see that if we want to go from negative pi to pi, so that means if we have this axis, so let's say we have this for one direction and this one for another direction. So that's between, so this is negative pi and this is pi over here. So we have this area plus this area over here. So we could see that, well, if we try to integrate this now, we could break this into two parts. Or actually, we could just go ahead and integrate this all together. So that's going to be sine x dx. So we would just have negative cos of x between negative pi to pi. And so that means we would just have negative cos of pi minus negative cos of negative pi. So just be a little bit careful with the signs here. It's pretty important, or it's very easy to get confused or lost with the signs. So we see, well, this one is just going to be negative times negative 1 plus negative 1. So we have a negative 1 plus negative 1. That's also the same as saying 1 minus 1, which is 0. All right, so that's for the first one. Now let's have a look at the second part, where we have the integral from negative 2 to 2 of x squared. So graphically, it would look something like this. So we have this parabola, although not very helpful, not the best drawing. So say here's negative 2. This is 2 here. Then that means we have this area here and this area here. Well, one thing that we could see, this is since the parabola is actually a symmetrical function, it's an even function, then that means this area is also the same as this area. So that means if we want to calculate this entire area, we could also say that, well, this is going to be 2 times the area of this portion here, and that would give you this area here. So one way you could actually do this is the standard way. So let's say we have negative 2 to 2 of x squared times d of x. So that's going to be a third x cubed from negative 2 to 2. So we have 8, so we get 8 over 3 minus negative 8 over 3. So we get 16 over 3. So that's for one way. The second way, so let me break this apart. We could also write this as 2 times the area from 0 to 2 of x squared times d of x. So this 2 comes from the fact that, well, the parabola here is a symmetrical function. So this area and this area are the same. So we could also calculate this area and then multiply that by 2 so that you also count for this area as well. So that means we would just get 2 by, so 2 times a third, x cubed from 0 to 2. So we would just get 2 times 8 over 3, which is going to be 16 over 3. So we see here that this area, 16 over 3, using the first way that we calculated, is also the same as this area over here that we have also calculated as well. So we could make a rule for integrals of even and odd functions here. So let's say for even functions, well, that means, so even functions being f of x is also the same as f of negative x. So examples being the parabola, the cosine function is also an even function. So those two are some examples of even functions. So that means, so if we have the integral from negative t to t, so the interval has to be symmetric about the axis, let's say the y-axis in particular. So of f of x dx, this is also the same as saying 2 times 0 to 2 of f of x d of x. So that's for the first rule. For the second rule, we have for odd functions, so we have that if f of negative x here, this is going to be negative of f of x here. So that means, well, the integral from negative t to t, making sure that the interval is symmetric about the y-axis of f of x d of x, this area is just going to be 0, which this one we could see from the sine function example. So we see that if here's pi to pi, so the distance between negative pi to 0 is the same as the distance from 0 to pi. So that means this area and this area, they'll cancel out with each other. So the area is going to be 0. Okay, so that's for this part. So we're done with the substitution rule. And now let's move on to the next technique of integration. So let's have a look at integration by parts now. So suppose we differentiate a function that is a product of two simpler functions. So let's say we have a function of f that is equal to u times v, where u and v are two functions. So that means if we differentiate both sides, we would get f prime, which is equal to u prime v plus u v prime. Now let's say we integrate both sides again. So integrate f prime, integrate u prime v, and integrate u v prime. So that means if we rearrange, but we also know that this part is going to equal to f. So that's f here. But we also know that f is uv. So that means uv here is equal to the integral of u prime v plus uv prime. So rearranging the equation a little, we want this as a function or as the integral itself. So we would have uv prime. This is going to be uv minus the integral of u prime v. Or alternatively, so we could also see this as a function of x. So say f of x is equal to, for example, g of x and h of x. So by the product rule, f prime of x is just going to be g prime h of x plus gx h prime of x. So differentiate both sides, or integrating both sides, my bad, you would get the integral of g prime of x, h of x, d of x, plus the integral of gx, h prime of x, d of x. Well, since f is g of x, h of x, so we have g x, h of x, which is equal to the integral of g prime of x, h of x, dx, plus the integral g of x, h prime of x, d of x. So we want this side. So that means the integral of gx h prime is equal to gx h of x minus the integral of g prime x h of x dx. So that is integration by parts in a nutshell. So let's try to evaluate some. So there are two methods that I would actually like to go over. One of them being the standard way of finding the integral. The second method is going to be by using a method called the tabular method, or the DI method, if you would like to call it. All right. All right. So let's have a look at this first one. So we have the integral of sine x, x times sine of x, d of x. So this is where the integration by parts will come in. So we see that we have a product of two simpler functions, this x and the sine of x. The easiest one that you would like to differentiate is the one that's a polynomial. Okay, because the one that involves a polynomial is the best one that you would like to differentiate. So we would have that, well, if u here, so we're going to say we have a function that's of the form u v prime. So this sine of x is going to be the v prime, this x is going to be the u here. So the u is going to be the x, and the v prime is going to be the sine of x. So we want the other quantities. So we want the u prime. So that means if we differentiate, we get 1. And we also want the v. So if we integrate, we get negative cos of x. So once we put it into the integration by parts, this formula, so the u here would just be the x, and we multiply by the negative cos of x, and then we subtract it by the integral of u prime, so which is going to be 1, multiplied by the v, which is negative cos of x, d of x. So that means we have this negative cos of x times the, or subtract, plus this time, the integral of cos of x, which is going to be positive sine of x. And plus c. So that is one way we could actually do this. The other way is by using the tabular method or the DI method. All right. So how this works is, so you do a similar table setup as the first one. So we have the D and the I. What we put on the D column is the function that we are going to be differentiating. So in this case, we're going to have x. And then you keep on going until you reach a 0 mark. So with the polynomials is nice because eventually you'll see that one of the value functions that you'll get is going to be a 0. And as for the I column, which is the column that you're going to be integrating, you're going to put the function that you're going to be integrating. So that's going to be our sine of x here. So, and then we also have, so the integral of sine x is negative cos of x. Integrate it once more, we get negative sine of x. Now here's one addition that we need to keep in mind. We also need to add the signs here, plus, minus, plus. So they're always going to be an alternating sign between the plus, minus on this column. So now what we see here, we're gonna take the diagonals here, so this x, and we're gonna multiply them together. So we see if we multiply x by negative, so actually I'm missing this x over here. So if we take this x multiplied by negative cos of x, we would get this part over here. If we take the negative one, so we also have to include this negative, and the sine of x here, by multiplying those, so I'm going to say take this, you multiply them, you get the sine of x here. So, and then you plus c, right? So let's have a look at the next one. So that's how the tabular method. So once you get this part, you're good. And you could just go ahead and go to the straight answer. Okay. So let's have a look at the next part. So the last example here, we have the integral of ln of x. So if we integrate, so it's not that clear here, okay? But here's one thing that would make it a lot easier. If we have the integral of 1 multiplied by ln of x dx, now that should make it a lot easier to have a look at. So let's go ahead and use the standard method for this one, because the next example we'll actually have a look at using the next few examples would involve integration by parts, but using the tabular method. So I actually mentioned it a bit earlier than I should have. Well, that's okay. So using the standard method, so let's say we're gonna let u be the ln of x. So we don't want it to be the 0 right away, be the constant 1 right away, because if you just do one step of it, you're gonna get a 0 right away. So that means the u prime here is going to be 1 over x. And if you take the v prime to be the 1, then that means the v is going to be the x here. So we're going to use the integration by parts again. So that means this integral would just become x ln of x. And then we subtract it by the integral of 1 over x by x. So one thing that I like to do if I'm doing the standard method is take this one, multiply those two so that you get this one, and then you go across to get this part here. And once you integrate the last one, so we have x ln x times the integral of d of x here. So that would be x ln x minus x plus c. And that is the integral here. Very good. All right. So as I mentioned, we're also going to be having a look at the tabular method. So as I mentioned, so we're going to use the DI method here to show how this works. So if we want to integrate, let's say x cubed multiplied by e to the power negative x. So I'm going to use the DI method here. So what we have here is, so the function that we're actually going to be differentiating here, so this is going to go under a D column, is going to be our x cubed. So this is going to be x cubed. And don't forget the plus or minus and plus or minus as many times as you need to. So in this case, we're going to have maybe about 4 times. So if we keep on differentiating this, we'll get, so we have 3x squared, we have 6x, we have 6, and I'm also going to need one more. So let me make a bit more room. Last one is going to be the 0 part, right? And then as for the second column, or the third column where I'm going to be integrating, I'm going to put the e to the power minus x here. So e negative x. And I keep on integrating. So I get negative e negative x, ex, negative e negative x, and then e to the power negative x. And then so we go diagonally for each of the steps. So we would just go 1, 2, 3, 4. And don't forget the signs as well. So if we were to integrate this now, we could just go ahead and put it in order. So we have, first one, we have positive x cubed. So negative x cubed multiplied by e negative x. The second one, we have negative 3x squared multiplied by e to the power of negative x. The third one, we get negative, so the negative 6 of x, e to the power of negative x, and then negative 6x, or e to the power of x. And that's all for this one. And then plus c at the end here. All right, so for the last example now, so we have the integral of e of to the power of x times cos of x. So we're also going to be using the tabular method in this problem here. But one thing that you should be slightly careful about. So if I apply DI method here, So if we have d and the I, so I'm going to be differentiating the e to the power of x, and I'm going to be integrating the cos of x here. And don't forget the signs here, which are also pretty important. All right. So I'm going to repeat e to the power of x, which if we differentiate, is still going to be e to the power of x. And the one that we're going to be integrating is the cos of x. So the integral of cos of x, which is sine of x, and then negative cos of x. So see here that if I go with the diagonal first, so I have that, well, if I say that this is equal to e to the power of x times sine of x, and then I have plus, no, yep, so plus e to the power of x times cos of x. But notice here, I stopped here on purpose. If I go straight ahead to here, so that means I'm still going to be doing negative of the integral of e to the power of x times cos of x d of x. So we're a little bit stuck here. But here's the thing. We have the same integral on the left-hand side, and we have this integral on the right-hand side as well. So why don't we bring this to the other side? So what we would have is that d2 times the integral of ex cos of x make this equal to e to the power of x sine of x plus e to the power of x cos of x. And then once we divide it by 2, then that means we would just get the e to the power of x cos of x dx. And this would just be equal to ex sine x plus e to the power of x cos of x. All this divided by 2. And that is, in fact, the integral of this example. So sometimes you'll have a repeated term that's on over here. So once you have that, you divide it by 2. All right, so that's going to wrap things up for this video. So if you have any questions, leave them in the comments down below.